Today, we are diving into one of the greatest detective stories in the history of science. Seriously, it's a mystery that stretches back 50 million years, and it's got a plot twist that for the longest time, nobody saw coming. Our mission? To solve the incredible case of the whale. And the central question here is just huge. I mean, think about it. The transformation is so complete, so totally radical, it almost feels impossible. So how on earth does an animal that walks on land become a creature that completely rules the oceans? And when you put them side by side, the differences are just, wow. You start with something kind of like a dog, 4 legs for walking, a coat of hair, living on land, and you end up with a sleek, hairless, aquatic giant. Its front limbs are now flippers, and its hind legs, they're gone. It's an absolutely epic evolutionary jump. So where do scientists even start trying to connect these two? Well, they do it with a really powerful set of investigative tools. You can think of it as forensic science, but for deep time. The scientists who do this are basically evolutionary detectives, and their specialty is reconstructing the family tree of life, a field known as phylogenetics. So the ultimate goal is to build one of these, a phylogenetic tree. Now, this isn't just some pretty diagram. It's a scientific hypothesis. For our purposes, it's the evolutionary detective's map of the crime scene, showing all the branching paths that life took over millions and millions of years. But how do you possibly draw a map when the original roads have been gone for eons? Okay, here's a fun way to think about it. It's called the Great Clade Race. Imagine every species is a runner in a giant branching race. As they run along their path, they hit checkpoints and get unique stamps in a passport. These stamps are really new evolutionary traits. Now, we don't have the race map. All we can see are the runners at the finish line today, and we can look at the stamps they've collected. By comparing who has which stamps, we can actually figure out which paths they took and who ran together for a while. We can literally reconstruct the race course. That's exactly how biologists use shared traits to rebuild the tree of life. And our detectives have one golden rule they live by. It's called parsimony. You've probably heard of it as Occam's razor. All it means is that the simplest explanation is probably the right one. So when they're looking at a bunch of possible family trees, scientists will always prefer the one that requires the fewest evolutionary changes, the one with the simplest, most direct path that connects all the evidence. All right, so our detectives have their map-making strategy and their golden rule, but with the whale case, a huge problem came up. You see, there were 2 main lines of evidence, the fossils and the DNA, and for a really long time, they seemed to be telling 2 completely different stories. And this basically created 2 rival teams of detectives. On one side, you had the morphologists, the classic detectives, dusting off old bones and studying the physical shapes of fossils. And on the other side, you had the molecular biologists, the high-tech forensics team, sequencing DNA and comparing the genetic codes of living animals. So what do you do when your 2 star witnesses, the bones and the genes, get on the stand and completely contradict each other? For decades, the paleontologists, looking at the anatomy, had one solid theory about who the whale's closest relatives were. But the geneticists, well, they were finding something else entirely, something wild. And this, right here, is where our detective story gets a massive plot twist. The molecular team, as they sequenced more and more DNA, started zeroing in on a suspect that, just based on appearances, seemed absolutely 100% unbelievable. The genetic evidence was just undeniable. It was clear, it was consistent, and it pointed to one very specific land animal as the whale's closest living cousin. And this conclusion was so out of left field that the fossil experts were, let's just say, extremely skeptical. Yes, the hippopotamus. Genetically speaking, that giant, semi-aquatic, river-dwelling hippo is more closely related to a sleek ocean dolphin than it is to a pig or a camel. This was an absolute bombshell. To the paleontologists, it made 0 sense. There wasn't a single fossil that supported such a bizarre idea. The 2 teams of detectives were at a total impasse. And then it happened. In the year 2000, a team in Pakistan made a discovery. It was a single fossil that changed everything. It was the smoking gun everyone had been looking for. And believe it or not, the clue was hiding in an ankle. The team unearthed the remains of a 47-million-year-old early whale called Rhodocetus. And this ancient whale had something incredible. It still had legs. And more importantly, it had an ankle bone. But this wasn't just any ankle bone. It had a very unique double pulley shape. Now, why does that matter?
because that specific shape was thought to be the one defining feature of a group of land mammals called artiodactyls, the even-toed hoofed animals like deer, pigs, and, you guessed it, hippos.
This one little bone was the missing piece of the puzzle. It was the aha moment. For the very first time, there was hard physical evidence from a fossil that proved what the DNA had been screaming all along. Whales didn't just come from some random land animal. They came from deep within this very specific group.
And just like that, the conflict was over. The two teams of detectives could finally shake hands. The ankle bone proved that whales are a type of artiodactyl, a weird legless swimming branch of the family tree that sprouted right next to the hippos. The mystery was solved.
Solving the whale's origin story is just incredible. But it's really just one story, one branch on this ridiculously enormous tree of life. The very same tools that cracked this case are what scientists are using right now to map the entire 4 billion-year history of life on our planet. And that history is it's almost too vast to comprehend. We're talking from the very first stirrings of microbial life almost 4 billion years ago, to the first complex animals, to the moment our distant ancestors first crawled onto land. In that grand scheme, the whale's dramatic return to the sea just 50 million years ago, that's actually a pretty recent event. And here is a really sobering thought to wrap your head around. The species that are alive today, they are just a tiny, tiny fraction of all the life that has ever existed. Paleontologists estimate that over 95%, 95, of all species that have ever lived on Earth are now extinct. The tree of life is always growing new branches, for sure, but it's also constantly being pruned. Which brings us to one final big question. We've spent all this time mapping 4 billion years of life's incredible history, a story of constant change, transformation, and loss. Many scientists now argue that we're living through a sixth mass extinction. So as we look at this immense ancient tree, the question isn't just about the past anymore. It's about right now. It's about the future. What will the next branch, the one that we are living on, actually look like?